has to interact with all three proteins. It has to interact with itself, has to interact with E1, and it has to interact with E3. So does that sort of answer the questions you were asking about what's the advantage of creating this monster complex? Now, this disulfide that is part of the structure of E3, right? This is an oxidized form of sulfur. This is a reduced form of sulfur. So the first thing it does is uses the oxidized sulfur to oxidize the reduced sulfur. Right? We just get an exchange, an oxidation-reduction exchange. Disulfide is reduced, dithiol is oxidized. Okay? That's straightforward. All right? And so now we've returned our lipoamide to its oxidized form. It's ready to go. But now we've got these two cysteines of the E3 in their reduced form. And that's where FAD steps in. FAD is involved in oxidizing that dithiol back to a disulfide. Now, here's what's not shown in the figure that we have to remember. What is FAD good at?
Doing it one at a time.
Yeah, it can do it one at a time or two at a time. When you're oxidizing thiols like that, that tends to be a one at a time oxidation. Right? That's why FAD is involved. It can oxidize one atom, it can oxidize the other one. They can come together to create a bond. FAD gets reduced. But ultimately, where does FAD want to send those electrons that it just took from this disulfide? To NAD. And what's NAD good at? 2 electron transfers. So FAD, we're going to see this over and over. FAD is going to play this role of being the intermediate between things that require 1 electron transfers and things that require 2 electron transfers. Right? So FAD is going to play that role, and it plays it very well. And so then we end up with the NAD being reduced. Everything is returned back to its start. Right? Any questions about what's going on stepwise?
It's then oxidizing the FAD, right?
Right.
Okay.
FAD gets reduced when these are oxidized, but then the FAD is immediately re-oxidized as NAD is reduced.
Is that written as FAD 2+ then? Or how does...
FAD is always neutral because it accepts an electron and a proton.
Oh, okay.
Right? Right.
FAD
Every
H2.
electron it accepts a proton with it.
So is it FADH2?
FADH2.
Okay.
So yeah, the intermediate here, there would be an FADH2 intermediate. Okay? Any questions?
So why this is all favorable because NAD being reduced is better than FAD being reduced?
Well, let's think about it, right? Because what do we know about reduced NAD? What do we classify that as?
High energy.
A high energy molecule, right? That's one of our high energy molecules. So anytime you end up with your product being a high energy molecule, you suspect that maybe this overall reaction is not favorable, right? But yet, doing the reaction in this direction is essential for the process to continue. So what is it that ultimately makes this favorable? We're making a high energy product. We've got 2 things that play to our advantage here that make this process tend to be favorable, even though there are reasons why we would suspect it wouldn't be. One thing that happens early, another thing that happens late. What? Well, sometimes we have a lot of substrate. I wasn't even going there. But yes, in any process, even if it's unfavorable, if you give it enough substrate, you can usually get it to go. We're in biological systems, so we can't way overload with substrate without putting other things out of balance. So we're limited in how well we can do that, but that certainly plays a role. That when we have a lot of pyruvate, this is more favorable. There's one thing.
Does the NADH get used up?
Where is NADH? What happens to the NADH in the mitochondria?
Electron transport chain.
What?
The electron transport
Electron transport chain. So if the electron transport chain is immediately oxidizing that NADH to make ATP, then the concentration of NADH is kept low, the concentration of NAD is kept high, and that tends to make this more favorable. That's one thing. What's the other one?
You're taking away the product.
We're taking away one of the products, right? Carbon dioxide being a gas, right? Even though it's soluble in the solution because of the action of carbonic anhydrase, ultimately carbon dioxide is removed, right? So it makes this reaction metathetical. We get a gaseous product which ultimately is removed from the potential equilibrium. Right? So we've got losing carbon dioxide tends to make it more favorable, which explains why we're willing to lose that carbon dioxide. And if oxygen is present, reoxidizing the NADH we make is making it favorable. Okay? Does that help? And Melanie, can you twist that just a touch? We got more board.
Oops.
That's okay.
Sorry.
And I think it's wider than it shows there. It records wider, so you should.
Oh, okay.
But I just see a lot of board and not enough of the overhead. Okay? So, does that make sense? Is that consistent with the things that we understand about chemistry? And we're getting a feel for the way these things should make sense chemically? Okay, let's see. That's showing some mechanistic stuff. I'm not concerned about that, not concerned about that, not concerned about that, given how far behind we are. This is showing part of that E3 enzyme. I just like this picture. This is a figure from your book, right? But here's that disulfide bond, cysteine 43 and cysteine 48, right? So that's the disulfide bond that's part of E3. This is the flavin rings of FAD positioned close to that. There's a tyrosine, which is alternately oxidized and reduced as part of the process, but then you can see NAD here close for the transfer of electrons to the NAD. Okay? I just think it's a pretty picture. Every once in a while we have to show pretty pictures. Okay. Sorry about the wordiness of this. It's available on that thing, so you don't have to try to write it all down. I was trying to keep this straight. Let's see. Do I have a better? I thought I had a better thing. We can go back to. Oh, whoever's watching this on YouTube is going to get dizzy. We can go back to here. It's a little tough to see. Right, so here is our pyruvate dehydrogenase. This is, again, a little pixelated because of the way I had to do this. So here's pyruvate dehydrogenase. It's got a particular serine that is used for control. So when that serine is in its free hydroxyl, that is the more active form. When that serine is phosphorylated, then pyruvate dehydrogenase is in its less active form. So pyruvate dehydrogenase, this is E1. So within the E1 subunit, there is a phosphorylation site, which is a control site for E1. Okay? So E1 is phosphorylated. Now, as part of the complex, there is a kinase and a phosphatase that are part of the pyruvate dehydrogenase complex. So it is the kinase that is part of the complex that is doing this phosphorylation. It is the phosphatase that is part of the complex that is doing the dephosphorylation. Okay? So, right, here's the kinase, here's the phosphatase. That's involved in control. So first, ATP. Before we even look at the figure, would we expect ATP to promote or inhibit the pyruvate dehydrogenase reaction?
Inhibit, right?
I'm just watching Sarah think about
I'm trying really hard not to look at the screen.
it. Promote or inhibit? Just what do we want to have? If we've already got a lot of ATP, do we need to send pyruvate through?
No.
No, right? I mean, that makes sense. For two reasons. One, we just don't need to be making more ATP if we've already got a lot of ATP, right? Given that the amount of ATP and ADP in the cell is a fixed quantity. But also, if we go past this step, if we go from pyruvate to acetate, then we can't take that carbon through gluconeogenesis anymore. Right? As long as we keep it at pyruvate, we can do gluconeogenesis. If we get to acetate, we can't do gluconeogenesis with it anymore, and we've wasted a carbon. And we've restricted what we can do with that carbon. Okay? So if we've got ATP, ATP tends to directly inhibit even the dephosphorylated form of pyruvate dehydrogenase. So it tends to inhibit it allosterically. But if the kinase is present, if we haven't taken the kinase out of the complex artificially, then ATP tends to activate the pyruvate dehydrogenase kinase. And by activating the kinase, causes the phosphorylation of pyruvate dehydrogenase, the E1, and therefore its inhibition. Does that make sense? Ellen's thinking about it. Question, Ellen?
Read it.
Huh? Yeah, it's tough to read. This is one you'll want to print out and look at.
There you
Oh, you pulled it up?
go. Yeah. I was making sure they were on there.
Were they on? So it's on there?
Yeah, there's 5 slides on there.
5 slides on there? Okay, so yes, this one's there. Now, what about, this is acetyl-CoA. This is an acetyl group, sulfur-CoA. We've got lots of acetyl-CoA. Where would that acetyl-CoA be coming from if it's not coming from carbohydrate metabolism?
Fatty acid metabolism.
Fatty acid metabolism or amino acid metabolism. So we've already got a lot of acetyl-CoA in the mitochondrion from other sources. What are we going to do to pyruvate dehydrogenase? Inhibit